I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Just pray you be with us today. Help us to glorify you, what we do, Lord. In your name I pray. Amen. So as I mentioned to you guys, I think we're going to take it easy on the quizzes for a while, and I'm going to give you homework instead. I'm working on putting that together. I should have it together sometime soon. So I should mention that again. So you can expect there'll be homework posted sometime soon. I'll make an announcement about it when it actually happens. All right? So let's talk about eigenvectors. Eigenvector solutions to dx dt equals to ax, right? And just to review, what's our procedure? Step number 1, identify the matrix of coefficients A and carefully calculate the solutions lambda 1, lambda 2, lambda n of the determinant of A minus lambda I equals to 0, right? What is this called? This is called the characteristic equation, right? Characteristic equation. The solutions to the characteristic equation are called the eigenvalues. All right? Eigenvalues are the solutions to the characteristic equation, right? Then step number 2 in our procedure was we find vectors non-zero, right, such that A minus lambda I ui equals to 0, right? That makes that u sub I a eigenvector with eigenvalue, stupid marker, with eigenvalue lambda sub I, right? And step number 3, you build your solution, right? Solution has the form what? X of t is like c1 e to the lambda 1t u1 plus c2 e to the lambda 2t u2 plus plus cn e to the lambda nt un, right? Now this is, so here I'm using the notation that the lambda 1 could be equal to lambda 2. I mean, these could be possibly repeated, all right? But it's worse than that, right? I mean, so we saw last time that we could have an eigenvalue of, what was it? Eigenvalue, trying to remember. I think eigenvalue, we had a matrix with eigenvalue 2, right? But we only had 2 eigenvectors for that one, even though it was a 3 by 3 matrix, right? So we have the general theory here says we're looking for n linearly independent solutions to a n by n problem, right? If I have n differential equations, linear differential equations with constant coefficients, the system, like I start with there, then I'm looking for n linearly independent solutions. I'm looking to construct the fundamental solution set. And so for that example we had last time that just had 2 eigenvectors, even though it was a 3 by 3, that was not enough to construct the general solution. We're missing something. And we also saw that for the example at the end of class, right? The little 2 by 2 one I constructed based on the repeated root case for the second order problem. That was also a 2 by 2 case where we only had one eigenvector despite the fact that we need two to construct full solution set. So we got to come to terms with what's missing there. But before we even get to that, there's another thing that could happen, right? These eigenvalues could be complex, right? So what happens then? What about when the eigenvalue is complex? How do we deal with that case? So there's these two remaining cases for us. The one is that the eigenvalues are complex. The other is that we don't have enough eigenvectors, real eigenvectors, right? There is then also a combination of those two cases. You could have, it turns out, not enough complex eigenvectors as well, but that's at the end of the story, so I'll leave it for there. So let's look at an example, just to get back into it. Well, actually, I shouldn't do that because we'll run out of time if I'm not careful. So let me show you the complex case. So if we have the determinant of a minus lambda I equals to 0 has solution lambda equals to alpha plus or minus I beta, where beta is not equal to 0, right? Then we can look at it as a complex problem. Then there exists u equals to a plus ib, all right, where we could say a, the real part of the vector u is a, and the imaginary part of the vector u is b. So a and b vectors are both real vectors, all right? And this u, what am I talking about? So I'm saying that you can still solve a minus lambda I times u equals to 0. Linear algebra says if that lambda is complex, all right, then there still exists a complex vector u that will solve this equation. This is called a complex eigenvector. Complex eigenvector. Now we need to make a choice, so we're not being ambiguous here. Let's choose the plus. All right? Choose the plus. I'm going to say lambda is equal to alpha plus I beta. They always come in pairs because the characteristic equation's a real polynomial equation. So complex solutions to real polynomial equations, they always come in complex conjugate pairs, right? You're never going to have a real polynomial that has like 2 plus I as a solution, but not 2 minus I. If you got 2 plus I, you always got 2 minus I. They come in pairs. So anyway, we can calculate this complex eigenvector, and then how do you construct the solution? Well, through the same calculus as before. So this is a calculus I did 2 lectures ago, right? Maybe, was that a test? Did I do this? I forget when I did it, but maybe, I think 2 lectures ago, so a week ago, we proved that if you have x equals to e to the lambda t u, right, then dx dt is equal to what? It's equal to lambda e to the lambda tu, and that's equal to e to the lambda t times au, right? But if u is an eigenvector, au is equal to lambda u. I'm sorry, I just did that. I'm an idiot. I was thinking that, and look what I did. I traded my lambda times u for au. Okay, I already made that step. But then, of course, this is just a times e to the lambda tu, right? So what does this line say? X equals to e to the lambda tu solves dx dt equals to ax, right? Just to just to remind you why we do eigenvectors is because of this string of calculus that proves that if you take e to the eigenvalue times time times eigenvector, you solve dx dt equals to ax, right? Don't forget, I mean, this is the theoretical bedrock on which we're building our house. But this calculus could just as well be thought of as in terms of complex calculus. Lambda could be complex. U could be complex. This calculation still goes through just the same. So you might say z equals to, so here this is, let me put a big parentheses around, this is a parenthetical remark. This is a reminder. Right, so now let me return to my complex story. If we put z equal to e to the lambda t u, right, this is a complex solution to dx dt equals to ax. So if you want to be picky, it's not really a solution to the given, technically speaking, it's not a solution to the problem as stated. It's a solution to a corresponding complexified problem. And that's fine because the calculus is really friendly to us here. You notice that if we have z, right, if it's equal to, say, if it's equal to x1 plus I times x2, right, where x1 is the real part of z and x2 is the imaginary part of the z solution. What happens when we calculate dz dt? How does dz dt look like? It's dx1 dt plus I times dx2 dt, right? We differentiate the real part and the imaginary part separately. This is how we differentiate complex valued vectors. But this is equal to what? This is equal to a times z, right? Because this calculus still works. But a times z is what? That's a times x1 plus ix2, which is equal to ax1 plus I times ax2. So what does this prove? This proves that if we have a complex solution to the problem, we get two real solutions. You're like, haven't you shown this already? Yes, I have shown this for different problems. I'm showing it again for this one, though. So this has to match that. This has to match that. Right? So we can pick off the real and imaginary parts of the complex solution as being distinct real solutions to the problem. Okay? Now let's expand on that. What does x1 and x2 actually look like here? What are x1 and x2 explicitly? So we have z equals to e to the lambda t u, right? Let's expand on that, though. That's e to the alpha plus I beta t times a plus ib, right? Which is e to the alpha t times cosine beta t plus I times the sine of beta t times a plus ib. Just trying to be real with you. No, it's okay. Okay. Someone was disgusted by that. I feel like I did my job. Good. All right, so this is e to the alpha t, and that's cosine beta t times a vector minus sine beta t times b vector, all right, plus I e to the alpha t cosine beta t times the b vector plus sine beta t times the a vector. So in a lot of differential equations texts, they won't tell you hardly anything of what I just said, because they don't think students can understand it. How dare they? Because, I don't know. But I think you guys can understand what I just did. And it gives understanding to why we use x1 and x2 as our real solutions to the complex case. This is where they're coming from. They're just the real and imaginary parts of a complex eigensolution. Huh, weird. So to every complex eigenvalue, we get 2 real solutions, right? So I have an example for us. Example 1. Let's look at x prime equals minus 5x minus 4y and y prime equals 10x plus 7y. All right, first order of business, we need to rewrite it as a matrix problem, right? So this is what? This is really x, y prime, minus 5, minus 4, 10, and 7. X, y. So here's my coefficient matrix, right? Here's A. So I need to look at the characteristic equation, right? Determinant of A minus lambda I, which is the determinant of what? It's minus 5 minus lambda minus 4. I'll put some dividers in here. 10 and 7 minus lambda. So that gives me what? That gives me lambda plus 5 times lambda minus 7 plus 40, aka lambda squared. I got a minus 5, excuse me, a plus 5 minus 7, which is minus 2. Yeah, plus 5. I said minus 5, but I was wrong. Oh, yeah, thanks. You guys are ahead of me. Good. Now we complete the square, as it reminds us of middle school. I'm sorry, that was a comment from my universe, perhaps not yours. Lambda minus 1 squared. So that reproduces the lambda minus 2, and it also adds 1. But I've got 5. So to be fair, I need to change the 5 to a 4. Yeah, 2 squared. So generically speaking, once you got to this pattern, this tells me that alpha is equal to 1 and beta is equal to plus or minus 2. I mean, let's just say beta equals to 2. So this gives me complex lambda of 1 plus or minus 2i. When you complete the square and you get a sum of squares, that means you got a complex solution. If you complete the square and you get a minus here, that means you got a real solution. Completing the square always works, though. If you complete the square and you got 0, it's a repeated root. Them's all the cases. All right, so now we got our complex eigenvalue. Lambda equals to 1 plus 2i, right? Now what's our next step in the procedure I just erased? The procedure is the same for the complex case, though. We now look for a complex eigenvalue. So I'm going to try to solve a minus 1 plus 2i I times u equals to 0. What's that look like here? Explicitly, that looks like minus 5, right? Let's clean it up. This is what? This is, we got what? We got minus 6, minus 2i, minus 4, 10, and down here we got what? We got 6 minus 2i. So it's harder to tell. It's harder to tell if you're right in this case. Like in the real case, it's pretty obvious when you have the same equation repeated for a 2 by 2 case, right? You can just kind of eyeball it. But here, it requires a little bit more courage to go on without checking. I will do that though. So this would say pick either one. They have to be the same equation. So minus 6 minus 2i times u minus 4 times v equals to 0. So we could solve this for v pretty easily. V would be equal to minus 6 minus 2i divided by 4, right, times u. Lots of different choices here. I guess we could simplify that a little bit. Let's do that. Make our life a little bit easier. That's what? That's actually minus 3 minus I over 2, right? So if you don't like fractions, what should you what should you make u equal to? Yeah, let's go with u2. Let's see here. Set u equals to 2. So then v is equal to minus 3 minus I, right? And so our vector would be 2 and then minus 3 minus I. Now, if we want to use the general derivation I just worked through, right, in terms of the a and the b and the alpha and the beta, well, we know what alpha and beta are already, right? But we need to find the a and the b, so to speak. That's not hard. All we got to do here is just go, okay, well, that's 2 minus 3, right, plus I times 0 minus 1. And so now you can identify, you can recognize that this guy is a vector and this is the b vector. Now we have everything we need, given the general derivation I just did, to write down the solution, right? So what's my x1? E to the alpha t, which is e to the t, right? And then I'm supposed to do cosine of, what's my beta? My beta is 2. Cosine 2t, right? And then my a vector was 2 minus 3 minus the sine of 2t. My b vector, 0 minus 1. And x2, e to the t sine 2t, 0, wait a minute. Yeah, 0 minus 1. plus the cosine of 2t. Now, if for some reason you forgot my formulas over there, you could rederive them, right? Because we can always fall back on the fact that we just take the real and the imaginary parts of the complex eigensolution. It's not that hard to work out, right? I mean, I can get these two using this, right? But the other way I could find these two solutions would be to look at e to the t, e to the 1 plus 2i t times the complex eigenvector 2 minus 3 minus I, right? If we look at that z, if we look at z equals to this, then the real part is that one, right? And the imaginary part is this one. But you either got to memorize these formulas, or you got to understand the real and imaginary parts of the complex solution. What you can't do is leave your answer as e to the 1 plus 2it times 2 minus 3 minus I. That's unfinished. We're looking for real solutions to real differential equations. So we use some complex math as an intermediary, but it's not the answer, right? So I still haven't written the answer yet. These are separate solutions. What's the general solution? We got C1 e to the t, and I'm going to go ahead and put some stuff together. So I get 2 cosine t, 2 cosine 2t, right? And then downstairs I've got, what do I got? Oh, I'm sorry. Yeah, minus 3 cosine 2t plus sine 2t. And then plus C2 e to the t. So all I'm doing is I'm just putting this stuff together, all right? So I got 2 cosine 2t here, and I've got minus sine 2t minus 3 cosine 2t. I don't always make this step of actually combining the things in parentheses. Like I'm usually okay with you writing your answer basically as just C1 times this thing plus C2 times that thing. That's also an acceptable answer. It's just I wanted to put them together to kind of give you a slightly better answer like this. So there you go. That's the vector form of the general solution to this problem. And while we're at it, yeah.
I was wondering for x2, should
Uh-oh. Yeah?
should the cosine and sine be switched?
Oh, yes, yes, I need to make up my mind. You're right. Now that I'm back here, I can see it. So, yeah, let's look at it that way. So this was supposed to be cosine, and this was supposed to be sine. So, I can derive formulas, but I actually need to also read them. Thank you. Now that does what? That changes this to sine 2t. Thank you for interrupting. Most appreciative of that interruption. Let's see here. This is cosine and sine. Sorry about that. Yes, details matter. Very good. So there's your general vector solution, right? And now we can find the fundamental solution matrix. What's the fundamental solution matrix here? We got e to the t, 2 e to the t cosine 2t, 2 e to the t sine 2t, down here, minus 3 cosine 2t plus the sine of 2t, all of that times e to the t, and then minus cosine 2t minus 3 times the sine of 2t, all times e to the t. And there you go. This is your your fundamental solution matrix for this problem. Yeah.
Where does the I go on the second part of x2? The I that was in front of E alpha t.
Well, I'm using the theorem, right? The theorem says, I guess I didn't finish writing the theorem, it's my bad. Theorem. If dx dz dt equals to az, then this happens, right? Thus, x1 and x2 are real solutions to dx dt equals to ax. So the I does not appear in the solution, and it shouldn't, because we're looking for a real solution. So we peel off the coefficient of I. That's the imaginary part. This is just like when we're solving before, right? We solved before something like y prime prime plus y equals to 0. We found y equals e to the it, which is cosine t plus I sine t is a solution, right? The I does not appear in the solution. It's the sine and the cosine. In the same sense here, that I doesn't appear in the solution. Was that actually your question? But yeah.
Which one would you like on the test?
Which one would I like on the test?
Like as a answer.
Oh, as the answer. It depends on the question. If I say find the fundamental solution matrix, then this one.
Okay, but if not, would you prefer the one on the left board or the one on the right?
I actually prefer this. It's easier for me to grade, but I wouldn't count that off, you know. And these are kind of a bear to grade also. There's like a lot of, if you work, two of you work a problem independently and then you compare answers. You could both be right and the answers could look drastically different. See, because what was our choice before for eigenvectors? We set u equals to 1 or 2 or something to get rid of fractions. Now, here we just set u equals to 2, right? We set u equals to 2, right? We could just as well have set u equal to I. Or 20i, or worse yet, something like 2 plus 10i. I mean, you can, really any non-zero complex number will make a choice of complex eigenvector. And the thing is, complex, what's complex eigenvector? If u is an eigenvector, right, if you have au equals to lambda u, then if you look at this, a times cu is equal to lambda times cu, right? But this c could be any complex number. What happens when you take any complex number and multiply by a vector? It's quite complicated what happens. Try it out. You'll see it's rotations, it's dilations, it's, complex scaling is not the same as real scaling. We have a geometric intuition for what that is. Real scaling is when you increase the length of the vector, or you reverse the length of the direction and go the other way, right? Positive, negative. You take a vector and you multiply it by I. What does that do? Just try it out. Here's the vector 1, 1. Multiply by I. What do you get? I. And then, visualize that. So you can't visualize that. Where is complex 2 space? How do you draw complex 2 space? See, the simplest system of differential equations, if you actually start asking geometric questions about the complex eigenvectors, you'll get stumped pretty fast. So we pretty much have to rely on algebra here. We don't really have an option. This is essentially, to understand that, we'd have to think about R4 or something. But even if you suppress R4 and just look at 2 of those dimensions, suppose you just suppress R4 and look at 2 of those dimensions, like this. So suppose that this is the other 2. other two. So this vector would have some piece of it that would look like this, right? And when I multiply by I, it rotates it up to here. You know? So complex multiplication is something like well, it involves rotation, but it's also involving like stretching. But you can't, it's complicated. So I don't know why I'm talking about all this, but my warning to you was just like, don't be sad if your really smart friend gets a different answer than you. Don't doubt yourself necessarily. You could both be right. You know? Okay. Point made. Any questions? All right. Another example. Example 2. We're going to solve dx dt equals to ax with a equals to 0, oh, I'm sorry, 5 minus 5, 3, 5 minus 3, 1, 3 minus 1, and 1. All right. An n by n matrix will always have n eigenvalues, possibly repeated, possibly complex. So we know that this is going to have 3 eigenvalues, right? That's a given. Okay, so can you guys tell me, see, something we could do to make this problem easier. What happens if we multiply a times 1, 1, 1? What happens with that vector? I get 3. I get 5 minus 3 is 2 plus, that's 3. If I look at this, I get 3. Yeah, 3's all around. So that's 3 times 1, 1, 1, right? So apparently, lambda 1 equals to 3. This is one of my eigenvalues. All right? Yep. Just looking at it. I mean, I made this example up so that would happen.
Yeah, no, but like, how are we supposed to get that?
Well, that would be a hint.
Oh, so you would give that to us?
Yeah, or it's a homework question, so you can use technology to figure things out. Yeah. More on that later. But yes, admittedly, I mean, good question. Good question. That is why 3 by 3s are hard. So anyway, you calculate the determinant of a minus lambda I, all right? And I'm not going to spend 20 minutes to do it, but if you do it, what does it work out to? It will work out to minus, parentheses, lambda squared plus 4 times lambda minus 3. Obviously, I'm omitting a few steps. You can write this in your homework, and I will omit a few points. So, okay, but our time is valuable in here, and you've seen me suffer through a 3 by 3 determinant already. Let's not repeat that. Okay, so we already know what the eigenvector with eigenvalue 3 is. What about this one? This one says that lambda 2 is equal to 2i, let's say, right? And you could think about lambda 3 being minus 2i. But if you look at what we've just done, it will suffice to just look at the 2i, not the minus 2i, right? You notice that? With the complex conjugate, we only need to use one of them to get everything we need. So what we need to look at then is a minus 2ii u. What's that? That is going to look like 5 minus, oh, why have I signed up for this one? 5, I should have made an easier problem. Goodness gracious, 3 minus 5, I'm going to regret this. Minus 3 minus 2i, yeah, why did I do this? Minus 1, I'm sorry, I'll stop. 3, 1, ay caramba. 1 minus 2i, yowzers. Yeah. Let's see here. I mean, when I'm faced with a problem like this, what I usually do is pick on the easier part. So what I do is like multiply this 3 times row 2, multiply this 5 times row 3, all right? And if I do that, why'd I do that? I do that so that they match up, you know? So then I can eliminate one of the variables from the, say, the third row, and that'll give me a simplified equation, which maybe that'll be enough to go and finish this thing, you know? We'll see. So then I can take row 3 minus row 2. What's that give me? So I'm leaving row 2 and row 1 alone. So those stay as stated. And what happens with row 3? Yeah, I get 0. Let's see here. So when that gives me 9 plus 6i minus 5, which is what? 4 plus 6i, right? And 2 minus 10i. That ought to do it at this point, actually, because this third equation is really all I need. This makes me believe that I'm pretty sure I can say that, 4 plus 6i times u, I'm sorry, times v, plus 2 minus 10i times w is equal to 0. And so at this point, I'm going to use w as my parameter, and I'm going to be able to, by setting w equal to a constant, it's going to force me to put u and v equal to something, and then I'll have my complex eigenvector, I think. So we try that out here. So let's see here. I have v is equal to 10i minus 2 divided by 4 plus 6i times w. So if we want to avoid arithmetic, what do we set w equal to? Set w equal to 0. That is the one thing we cannot do. Any choice but that one. Let's see here. So let's 4 plus 6i seems like the laziest possible choice. If I do that, then I already know what v is. V is equal to what? 10i minus 2, right? And then how do I find u? Either one of, I mean, you pick your favorite equation, whichever one you want, we can figure out what u is, right? How about, let's go back to, this one seems nice. So that says what? That says that 3 times u minus v plus 1 minus 2I times w, right? So that means that u is 1/3, that's 0, u is 1/3 of v plus 2I minus 1 times w, right? So u is 1/3 of 10I minus 2 plus 2I minus 1, what was my w? 4 plus 6I. Which is 1/3 of, I'm going to multiply this out before I try to do anything else, 10I minus 2 plus 8I minus 12 minus 4 minus 6I. Put my i's together. 18 minus 6 I got. Looks like I got a net of 12 i's, and so this sort of episode from Naruto. Let's see here. Minus 18. Oh, hey, that's nice. That's nice. Minus 6 plus 4I. Okay, so let us collect our thoughts. What's my complex eigenvector? I've got u equal to, what was my u? Oh, this, yeah, minus 6 plus 4I. What's my v? Minus 2 plus 10I. What's my w? 4 plus 6I. So you can see that that is going to be minus 6 minus 2, 4 plus I times 4, 10, 6. There are 3x3 problems, all right, that are more reasonable for tests, where this doesn't happen. All right, there are 3x3 problems where you end up with a few zeros, and it makes it much easier to do the algebra here. Like, I had to actually think about this algebra. And I would usually just, I was on the cusp of falling back to technology to do this, but I thought it'd be good to try to work through it, and I'm glad we succeeded, but I'll admit I was worried we weren't. So, I mean, this could still be wrong. Here's A and B. I mean, I've made a lot of steps, right? But anyway, there's your A and your B, and so the general solution, x equals to C1 e to the, well, I'll do the easy part first, e to the 3t, 1, 1, 1, right, plus C2, and the eigenvalue here was complex, right? But more specifically, it was pure imaginary. We love pure imaginary. That means that there's no e to the alpha t term in the solution that I just erased. It's just you got your cosine 2t times minus 6 minus 2, 4, right? You got your minus sine 2t, 4, 10, 6, and then plus C3 sine 2t minus 6 minus 2, 4, plus the cosine 2t, 4, 10, 6. And yeah, I think that if you can get to this, I pretty well can see that you understand what you're doing, and I will take that as an answer. Yeah. So we can also have complex in a 3x3 like that. Any questions? So, complex eigenvalues are kind of a mixed blessing, right? Because when you have a complex eigenvalue, that's a 2 for 1, You get 2 solutions at the cost of 1 eigenvalue. So there's only one eigenvector to find. In contrast, when we had 3 distinct eigenvalues for a 3 by 3 last time, that required us to find 3 separate eigenvectors with 3 separate calculations. But those 3 calculations, in some sense, are easier than this one, too. So it's kind of a mixed, Where's the question? Comment? Yep.
How do you get the sine of 2t and cosine of 2t? Is that?
That goes back to the solution that we derived. This is the real part, and this is the imaginary part of the complex eigensolution. Yeah. All right. Great. So we can solve complex eigenvalues just fine now. Well, I'll give you some homework, and you'll get better at it. The neat thing, you guys, is that I can actually test all of the cases. Yeah. Well, you got options here. Notice I kept the vectors in place this time. So this is sine times A plus cosine times B. And I can't make up my mind. So at this point, I have to cross this out, because we're no longer talking about that. I will now talk about the matrix exponential. So what is the matrix exponential? Definition. If A is an n by n real matrix, actually that's not required, but let's just say it's real, then e to the t, well, let me let A be m for a second here, m. E to the m, all right, is equal to I plus m plus 1/2 m squared plus 1 over 3 factorial m cubed plus dot dot dot. That is, e to the m is defined to be the sum k equals 0 to infinity of m to the power k over k factorial. Our usual application is to choose m equals to at. Most often, we set m equals to like t times a, usually. That's usually how we use this thing. So when I think about the matrix exponential, I'm usually thinking about e to the ta, like that. So let me show you an example. Consider j equals to 0, minus 1, 1, 0. So what's j squared? So if we multiply that matrix by itself, we get back to minus 1, 0, minus 1. Of course, that's equal to minus the identity matrix, right? So if we calculate j cubed, we get j times j squared, which is j times minus I, which of course is just minus j. What happens when we calculate j to the 4th? Yeah, j squared, right? Yeah. Also known as minus I times minus I, right? Which is I again. So this matrix J has order 4. After its fourth power, it gets back to the identity matrix, right? So this is a very interesting matrix to calculate the matrix exponential of. If we calculate e to the tj, then we have hope of actually calculating it directly. See? So this is I plus tj plus 1/2 t squared j squared plus 1/3 factorial t cubed j cubed plus 1/4 factorial t to the 4th j to the 4th, and so forth. So I can collect things, right? I've got I times what? 1, right? J squared is what? J squared is minus I, right? So that gives me minus t squared over 2. And then j to the 4th is I, so I get plus t to the 4th over 4 factorial. Dot, 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 right? And then I've got a j. What's with j? Well, I've got t, right? This j cubed, what was j cubed? Well, j cubed was minus j, right? So that gives me minus t cubed over 3 factorial. And if I'd kept the next term, we'd have got a plus t to the 5th over 5 factorial, and so forth. Can you guys tell me what those things we just calculate? What are those? What is this? This is the power series expansion of what? Cosine t, very good. And this is the power series expansion of sine t, right? So in this case, which is rather special, we can actually calculate the matrix exponential, and we get cosine of t times I plus the sine of t times j. Which, if we go back to our matrix, that's cosine t 1, 0, 0, 1 plus the sine of t times 0, minus 1, 1, 0. So it's actually the 2 by 2 matrix cosine t minus sine t, sine t, cosine t. So there you go. That's the matrix exponential when we use j, exponentiate j. Hey, that's a rotation. So this actually illustrates that a matrix of the form 0, minus 1, 1, 0 generates a rotation under exponentiation, whatever that means. What does this have to do with differential equations? What is this matrix? What's this J matrix reminiscent of? What coefficient? This is the this is the first problem we solved, actually. This is the problem we solved at the start. Remember? Do you remember what we solved to start with? We said x prime equals to minus y, y prime equals to x. That was the first one we solved by ad hoc methods. We substitute one into the other. That has matrix what? That actually has coefficient matrix that I have labeled J for this example. It's not an accident that we get solutions. Now it doesn't quite, well, anyway. This is not a coincidence. I'm not going to fully explain it at the moment, though. I should go on here, and actually, continuing, I should show you other properties of the matrix exponential. But apparently, it has something to do with, that's a solution matrix, right? This is a solution matrix for our, remember, what was the solution to this? Was what? X equals to, like, oh, I forget at the moment, but